Massimiliano. Welcome everyone to this Seamless Research webinar where we have the pleasure of receiving Massimiliano Marcellino. He's a professor of econometrics at Universidad Bocconi and a CPR and IGIER research fellow. Previously, he was an associate professor of econometrics at Bocconi and a professor at the European University Institute of Florence. And he has been visiting fellow at the University of California, San Diego, and Harvard University. He holds a degree in economics and social sciences from Bocconi and a PhD in economics from the European University Institute of Florence. He has published extensively on econometrics, time series analysis, and applied macroeconomics. And he is currently an editor of the Journal of Forecasting and associate editor of the Journal of Business and Economic Statistics and coordinator of the European Forecasting Network. He has worked as a consultant for the ECB, several national central banks, the European Commission, Eurostat, and the IMF. And as some of you know, he will be also serving as an advisor for some of the projects that some central banks from Latin America and the Caribbean are developing on forecasting topics. So he will be working closely with those of you developing these research projects. So without further ado, let me leave you with Massimiliano Marcellino. Thank you very much.
Well, thank you very much, Alberto, for the presentation. It's a big pleasure to be with you, and it's also nice to be connected long distance, even though I would, of course, not mind being physically there with you. So I am not a big expert on this platform, but if you have any questions, please just interrupt, and we will see how we can arrange it. So with Alberto, we discussed about what to present, and I thought that rather than presenting, say, a very research paper, it might be more interesting to give a kind of overview of the work that I have done on a particular type of econometric model that can be useful for a variety of applications. As we will see, both reduced form like forecasting, but also for more structural applications, so that perhaps this could be more interesting and relevant for many of you, okay? And so this is basically factor modeling. So basically, why factor models? Well, from a kind of statistical point of view, these are models that have a long tradition, and they are based on a decomposition of each variable, say xit, into a common component, that is this lambda ift that you see there in this equation, plus an idiosyncratic component. And the idea is that basically the common component is driven by very few unobservable factors. And so in addition to these very few factors that are driving each variable also has its own idiosyncratic component. So basically, from a statistical perspective, this is an interesting model because, as we will see, there are nice ways to estimate it, even if it is a nonlinear model. But it's also a kind of pretty relevant model from an economic point of view, because this structure where you have a variable that is driven by a set of key economic shocks is implied by a lot of economic theory. And so if you think about real business cycle models or DSG models, typically there are very few shocks. So here I put productivity, demand, supply, you can think of monetary, fiscal, and so on, that are basically affecting all of the variables in your system of economic variables. And another nice feature of this model is that it has very few parameters compared, for example, with the VAR model. And so you can use this model also for very large data sets. So here you have capital N variables, and this capital N can be very large. So you can have hundreds of variables. And so this is pretty convenient whenever you want to model basically large information sets. And of course, this is then again very relevant. Okay. Now, from a purely econometric point of view, these factor models have a nice set of features. So as I was telling you, with respect to standard VARs, they have much fewer parameters, and so you can estimate much larger models. And so an advantage, sorry, of estimating these larger models with many variables in them is that they are less prone, less subject to omitted variable bias and to more technical issues of non-fundamentalness of the shocks. And another nice feature of these factor models is that they are more robust than other models like VARs when you have structural breaks. And in particular, not so much the loadings, but the factor estimators are pretty robust in the presence of breaks. Basically because, as we will see, you estimate these unobservable factors by using the cross-sectional dimension, so the capital N dimension rather than the temporal dimension. And so this helps. And another feature nice with respect, for example, to panel models is that you can have very little requirements on the errors, on these psi-t that were the idiosyncratic errors. They can be correlated over time, heteroscedastic, a little bit correlated also across units. And so this is also an advantage. And the final advantage is that, as we will see, at least in the basic versions, these models will also be, say, pretty easy to estimate. Okay. Now, what can you do with these factor models? So, a kind of basic version, which is the earlier uses of the factor models, are basically to just summarize the information in a large set of indicators. So, for example, you could get a set of coincident variables like employment, industrial production, retail sales, surveys, income, some financial variables, and you could summarize them into a single factor that would give you a kind of coincident indicator of economic conditions. Or you could aggregate like this a set of leading indicators and get a leading index. Or you could construct, for example, financial condition indices. And for example, one of the most used indices for the US is one constructed by the Chicago Fed. So the National Financial Condition Index for the US is actually just based on a very big factor model with a lot of these financial indicators summarized with a factor model. So this is a very basic but already a very important practical use that you can do with it. Now, a second use is more related to what we will want to do with some of you, and so it is really nowcasting and forecasting. So the idea is to summarize these large information sets that you may have by means of a set of factors, and then basically to use the estimated factors, possibly in combination with the AR terms and other key selected variables, for forecasting your target variable of interest. Okay? And in general, they work pretty well. And so this is another nice feature. And so again, a little bit as what happened with VARs that first were used for forecasting and then for structural analysis. Also in this literature on factor models, people started with using these models for forecasting, and now more recently, starting maybe with the paper that if we have time we will look at by Bernanke, Boivin and Elias, they also use them to basically identify structural economic shocks and their propagation. And here again, contrary to small VARs, you have the possibility of identifying the effects of structural shocks on a very large number of variables. So they give you a more granular view on the impact of structural shocks on the economy. Okay. So what we will see together is basically first small-scale models that are a good introduction to bigger models, and then focus maybe on bigger models, so representation, estimation. Perhaps on estimation we will skip some parts because we do not have so much time, also if we want to keep some time at the end to ask questions. And then we will discuss selection of number of variables, and of factors in particular, and discuss forecasting and structural analysis. Okay? So here is a final bullet point in this slide. I have put a few references to surveys. So in particular, these ones by Stoker Watson and Lutekpohl, you may find them useful if you want to do more work in this area. So we will not have time to talk a little bit about extensions, but I wanted just to mention a few extensions that you may find interesting if you want to use this type of models for real work, so for applied work. Okay? So one issue that, as I'm sure you are all aware, is the need to try to basically also introduce parameter time variation, a little bit as it is done in VARs. So in here, I have done some work actually with people from the Bundesbank on how to introduce time variation in factor augmented VARs. And then, as you may have seen at the end of this presentation, I have put all the references, so you also have them easily available. So if you are interested in time varying factor models, if you look at this paper and the references in there, you find a kind of a primer on time variation in factor models. Now, something else that you may want to do is to deal explicitly with integrated variables. So typically in this early generation of factor models, there is an assumption of stationarity of the variables, weak stationarity. And in later developments, instead, I1 variables in factor models can be considered. And this parallels a little bit the literature on panel models and panel VAR models with I1 variables. So something that was a little bit missing is how do you put co-integration in these factor models. And so basically this is possible. And like you have factor augmented VARs, you can also have factor augmented error correction models. So we have done a lot of work on this with Anindya Banerjee and Igor Masten. And again, I've put some references in here if you want to have a closer look at this type of model. Then the third bullet point in this slide concerns with a practical situation, which is that typically these large data sets will be unbalanced. So they can be unbalanced because maybe some indicators have only been introduced more recently, like financial indicators or surveys. They can be unbalanced because you can have some missing observations in some periods. They can be unbalanced because maybe some indicators are monthly and others are quarterly, or they can be unbalanced because of a kind of asynchronous release of the indicators. So typically the surveys are more timely than, say, inflation or nominal variables, which in turn are more timely than real variables, and so on. So there are ways to basically use this type of factor models to try to fix these data irregularities that basically give you an unbalanced data set. And so to use factor models, like roughly speaking, extending Shaolin procedures, and using all the information that you have in this big data set to fill in this kind of holes that you have in the unbalanced data set. Okay? So here I've put the references to this work with Christian Schumacher, who is also at the Bundesbank, and again in there you find many more references on how to use factor models to deal with data issues. Okay? Now, another interesting extension that it is receiving enough attention is how do you put hierarchical structures in a factor model. So, for example, if you want to look at all the countries in Latin America, you may imagine that you have some global factors affecting all of them, some kind of factors that are specific to Latin America, and then you have factors that are specific to each country, and then you can even go more disaggregate, and so have regional factors, sectoral factors, and so on. And so this kind of more granular but still kind of hierarchical structure can be pretty interesting. For example, if you want to assess like, I don't know, like oil shocks affect a specific country or a specific region. And so you may expect that you have global effects, regional effects, country effects, and so on. And so here we did some work with people at the ECB focusing on the euro area and on the transmission of monetary policy shocks to inflation in the different regions of the euro area. So going within the countries, because one issue is that in the euro area, as in many other big economic aggregates, typically you have much more heterogeneity at the regional level than at the country level, and also the ECB was interested in assessing the transmission of monetary policy not only across countries but also across regions. And again, you can do this type of analysis with a little bit more sophisticated versions of the factor models that we will see together. Then the second bullet point in this slide is something very practical from a forecasting point of view. And the idea is that basically these factors summarize large information sets, but the summaries that you get are not necessarily specifically targeted to a variable of interest, like to inflation or to GDP growth. So there are ways to extract this information, these factors, in a more clever way, such that the factors instead become targeted, for example, to forecasting inflation or to forecasting GDP growth. Okay? And here we did some work with Christian Heppenstreich, who is instead at the Swiss National Bank. And again, in this paper, you find references on how to get these targeted factors. And also, this will be a pretty simple approach to follow. And then finally, for those of you that are maybe more interested again in structural analysis, and so when you want to do GMM estimation or IV estimations, you can also use these estimated factors as instruments. And typically they tend to work pretty well. So here again, I put this paper and you have more detailed references at the end of the presentation. So if you look at that paper and the references in there, they give you a kind of indication of how to use factors as okay. So then again, these are interesting extensions, but we do not have enough time to go in details through all of them. But if you are interested, you find the references at the end of the paper. So now instead, let us try our analysis of the factor model. And so let us have a closer look at the representation. Okay. So here, basically, your x variables are the variables that you are interested in. So let me put a pointer. So here you have your x variables. These are the variables that you want to model. Okay. So each variable that you want to model is affected by these unobservable factors. So f1, f2, f little r. And typically this little r, so the number of factors will be much, much smaller than the number of variables that you are analyzing. So for example, you could have just three factors, say demand, supply, and monetary shocks. And basically the effects of your three factors on the variables is governed by this matrix of loading, so these lambdas. So lambda 1, 1 is the effect of the first factor on variable 1, lambda 1, 2 is the effect of the second factor on the first variable, and so on. Okay? And then each factor, each variable x will also have its own idiosyncratic error, so something that is not common to all of them. And this size, again, can be partly correlated over time and across the unit. Okay? A little bit, not too much across the unit. Now, in small models, typically you take a parametric approach, and so you also specify a model for these unobservable factors that typically will be a VAR. So you see that here you have a model for your R factors that is, in this case, just a VAR1. And so in this A matrix, you find basically the dynamics of the factors. And then you have the shocks that are driving the factors. So here you have little r shocks. So at this point, this will be, say, reduced form error shocks that you may try to identify, and so to pass from the use to structural shocks like demand, supply, and monetary. And then you can study the transmission of the structural shocks exactly as you would do in a structural VAR, but you see that basically you will get the effects on your factors ft, and then you will get the effects also on the variables, because the shocks to the factors through the loadings will be transmitted to your variables. Okay. So this representation, again, so this is just a summary of what I was telling you. So within the axis, you get a large set of macro financial variables, for example, for a country, and the factors are their common drivers. Or you could use them for kind of multi-country applications. So for example, you could get a set of the GDP growth for many countries, and this basically, at this point, you would extract a kind of global cycle, okay? Or you could put, third bullet point, you could put all the subcomponents that you have in a consumer price index and assess whether the common forces tend to move strongly with aggregate CPR. Or you can get interest rates at different maturities, and then you put three factors, and these are the usual level, slope, and curvature factors that you find in term structure models. So basically, you see that there are really many interesting economic applications that you can do with this type of models. So let us try to use a more compact notation that will be convenient later on also for estimation. So basically, you can group all of your n variables into this vector xt. Okay, so xt basically here is basically just the column vector with all the variables you want to analyze. Same thing into ft, you group your three factors for period t. All the loadings go into this matrix lambda. All the idiosyncratic errors go into this vector xit. All the shocks to the factors go into the vector ut. And then again, you only need to make some assumptions on these xi and u's, so the vectors of the errors to the variables and to the factors. So here you find an assumption. And then you need some little bit more technical assumptions on the evolution of the factors. So as I was telling you, in the basic version of this model, the variables are assumed to be weakly stationary, so they must be driven by stationary factors. And so these conditions on the A matrix, or better on the eigenvalues of the A matrix, or even more closely to the eigenvectors of the matrix, are just conditions that guarantee stationarity of the factors and the fact that the factors have some dynamic. Okay, so they are not IID, and this is needed to differentiate basically the slightly persistent or more persistent factors from the idiosyncratic errors that are instead the XIT errors that you want to look at. So you can at this point write your model as you see in these two equations. And here again, this lambda f is the common component that is a vector. So you get one common component for each of the n variables. Psi t is the vector of idiosyncratic components. And this is called a static factor model, or a static representation for a factor model, because you see that basically the common factors only contemporaneously affect the variables. Now you could put more legs of the factor, so go to a dynamic factor model, and you can also put more legs into the VAR for the factors, and you can put deterministic components. All of this is basically no problem. Then in terms of notation, if you assume that your idiosyncratic error, so the elements of psi t, are completely uncorrelated among themselves, you get what is called a strict factor model. While if you allow for some correlation among the elements of psi t, so among the idiosyncratic components, you get an approximate factor model. Okay? Also, so here we have our model for the axis that you see in this previous slide, the VAR model for the factor, so for the FT. So basically this gives us, last bullet point, a parametric specification of the factor model. So you have an equation for the link between the axis and the factors, and another set of equations for the evolution of the factor. Okay, now an even more compact formulation. So basically, before we have aggregated over the temporal dimension, now we also aggregate over the cross-sectional dimension. And so basically now we put into this X matrix here basically all the variables and all the observations for each variable. And into this matrix F you put all the R factors and also all the temporal observations on them. Lambda remains the same as before, and now Xi also becomes instead a matrix that contains all the temporal observations for all the n idiosyncratic terms. Okay? So this is just convenient if you have to program estimation or if you just want to have a very summary notation. Okay. Now, it is also convenient to talk a little bit about identification. So using the notation that we have just introduced. So x is equal to lambda f plus xi. So the problem here is that basically your factors f are unobservable, and the matrix lambda of loadings, these are also parameters. And so the problem is that maybe if you put, maybe here it's a better indication, if you put a P matrix that is invertible between lambda and f, you get a model that has exactly the same likelihood as your original model. And so this tells you that you have an identification problem. So knowing the axis, you cannot uniquely estimate the lambdas and the factors. Sorry. This is a little bit as when you have an error correction model and you have alpha, beta prime, xt minus 1, and so you cannot identify the loadings and the co-integrating vectors without a priori restriction. Okay. So what is the solution? Basically, the solution is to impose some restrictions. And so you see that you can restrict either the loadings, so you put an identity matrix that basically will constrain the first subgroup of loadings, and or you put restrictions on the factors. So typically you put this restriction f prime is equal to the identity matrix, and this basically implies that the factors are orthogonal, so uncorrelated among themselves, and they have a unit variance. So this is not such a restrictive assumption, because since these factors are again unobservable, it makes sense to assume that they are also uncorrelated among themselves and with unit variance. So this is just a kind of scaling condition that doesn't change much. Okay, so if you want to know a little bit more about these identification issues, if you look at this survey paper by Lutekpohl that you see here in this final bullet point, it will tell you a little bit more, because there are some a little bit more sophisticated issues, like sometimes you can get estimators for the factors that are unique, but still the model is not completely identified. But this gets a little bit technical, so we can just skip. Now, in the next slide, there is, I think, an interesting question. And so the issue is this. We are used to working with vector autoregressive models, because we know everything about them, because we know that if the variables are weakly stationary, they admit a walled representation, so an MA infinity representation that I can invert and I can get a VAR. Okay, so the issue is, can I get a factor model that is equivalent to a vector autoregression? Or the other way around, can I find a VAR that is equivalent to a factor model? And unfortunately, in general, the answer is no, in the sense that if the data generating mechanism is a factor model, you cannot find an equivalent finite order VAR that represents the variable. Okay. However, what you can do, and you see it in this next slide, is work with a VAR model that is pretty similar to a factor model. So in this slide, basically in this first equation, you find basically a VAR, xt is equal to b xt minus 1. What you can do is you can assume that this B matrix that controls the dynamics can be decomposed into two matrices, C and D. Each of C and D has reduced rank. So if you now replace B with C and D, you get a model like this. So you get that xt is basically driven by C and gt minus 1, and this gt is a VAR. So if you look at these two sets of equations, they are pretty similar to the factor model that we have seen before, except that now these little g's are observable factors, because they are just a particular combination. They are just equal, as you see here, the gt are equal to d times xt. Okay, so this is called a multivariate autoregressive index model, and it has attracted some attention in the literature. The problem is that it is pretty more difficult to study this model than the factor model that we were considering before. If you may be interested in looking at this, in these couple of papers that we have done with two co-authors, you find more references. But again, since it is more difficult to estimate in particular, let's go back to our factor model xt is equal to lambda ft plus xit, and let us discuss estimation of this model. Okay? Again, let us start with a small model first, and then we will see what happens if instead you have a large model. So what you find in this slide is exactly the factor model parametric representation as we have written it before. So xt is equal to lambda ft plus the idiosyncratic errors, and ft is a VAR1 model. So if you look at the model written like this, you see immediately that the model is already in a state space form. And so in particular, x's are your observable variables, and unobservable factors ft are the states of your system. And so basically the first set of equations will be your observation equations. They link the unobservable states to the observable variables, and the second set of equations, those for ft, are the transition equations that basically are the state equation that govern the evolution of these unobservable states. And so basically, since your model is in state space form, you can directly apply the Kalman filter to get optimal estimates of the unobservable states, and then to get the likelihood of the model, and by maximizing the likelihood of the model conditional on the factors, on the estimated factors, you also get estimates for lambda, the matrix of loadings, for A, the matrix that controls the dynamics of the factors, and for the variance-covariance matrices of the idiosyncratic errors and of UT. Okay, so just using the Kalman filter. So this is basically what I was just telling you, and this paper by Stock and Watson is a very nice example where basically they use this type of model to construct a coincident indicator for the United States. Okay, so similar techniques can be applied for any country. There are, however, a few problems. Okay, the first problem is that when you have many variables, basically from a purely computational point of view, running the filter becomes very heavy. And so the typical applications of these parametric version estimated by the Kalman filter is for very few variables. In this paper that I mentioned by Stock and Watson, they only work with 4 variables. Okay? Now, a second problem is related with the quality of the estimators that you get for the factors. So if n is finite, so if you only have your 4 or 5 variables, you cannot get consistent estimator for the factors. At most, you can hope to get unbiased estimator for the factors. And so here the problem is that the factors that you're trying to estimate are random variables. They are not just parameters. And so this implies that you cannot hope to estimate them consistently, okay, with a finite number of variables n. Finally, as we have seen, to write your model in state space form, you need to write the state equation, so a model for the unobservable factors. But exactly because the factors are unobservable, it's not obvious to write a model for them. So here we are assuming that it is a VAR model that generates the factors, but since the factors are unobservable, it's very difficult to assess empirically whether this is a good idea or not. Okay, so what would we like to do? Basically, we would like to find an alternative model and an alternative estimation method that basically allows us to avoid these three drawbacks that we have just seen. So we would like a model that works well even if the number of variables n is very large. We would like to get consistent estimators for the factors, and we would like to have a factor model that does not require to estimate a parametric model for the factors. Okay, so a model that works whatever is the generating mechanism for the factor. Okay, so let us see if we manage to get a model like this. And so here we start analyzing this model in the next slide. Okay, so we want a non-parametric large N factor model. And in the literature, there are basically two competing approaches to study a factor model like this. One is associated with Stokes-Watson, and the other one is associated with a group of people, typically Mario Forni, Kalman, Marco Lippi, and Lucrezia Rankin. Okay? So we will see at the main features of these two approaches. So Stokes-Watson, starting with this because it is simpler, and then maybe I put some slides about the Forni et al. Approach, but since it gets a little bit perhaps too complex, I will try to just give you an intuition of what is going on. Okay, and then you have the slides and appendix with a few additional details. So let's start with the Stokes-Watson model. So you see that basically the model is very similar to the one that we have seen before. So xt is your set of variables, and now you can have many variables into xt, and all these variables are driven by these unobservable factors, so exactly as before. So now you do not have a model for ft. Ft can be basically whatever you want, but it must be weakly stationary. So to handle this level of generality, you need to impose some a little bit more complex conditions on the idiosyncratic components, on the factors, on the lambdas, and so I'm not going into the details of this, but if you are interested, you can look at these two papers by Stokes-Watson, and you get additional details on this. So the problem for estimation in this model is that both the loadings lambda and the factors f are unobservable. So basically this becomes a nonlinear model because you have this term lambda multiplied by ft that is a multiplicative term, and it is a function of two unknown objects, the matrix of loadings lambda and the unobservable factors. And in addition, these unobservable factors are random. Okay, and so this creates a complication. So how can we set up the problem? Imagine that we just want to find least squares estimators for the lambdas, so for the loadings, and for the factors. So what would you do? Basically, you would minimize the sum of squared errors, which is the kind of loss function that you find here. Okay, so xt minus lambda ft, so what you find here is basically just xit. Okay, so it's just this xit that you find up here, so are just the errors. So you are basically still minimizing a sum of squared errors. Okay, what do you want to get out of this minimization? You want to get all the lambdas, all the factors, and the factors for each time period. Okay. Now it turns out that even if the problem, this minimization problem, looks a little bit complex, there is an analytical solution. This is a kind of well-known problem in the statistical literature. And in particular, it turns out that the estimators of the factors that you obtain from this minimization of squared errors tells you that the factors can be estimated by taking the first R principal components of the variable. Okay? And in particular, the principal components will give you consistently estimators for the factors, or say a little bit more technically for the space spanned by the factors, because we have seen that the factors are not uniquely identified. Okay. So this tells you how to estimate the factors, and then once you have your estimated factors, you just regress, basically say your axis on the estimated factors that you have obtained, and this will give you also OLS estimators for the loadings. So basically estimating the factor model becomes pretty simple. Now, what else would you like to do? Well, you would like to determine how many factors you have in your model. So here you can either make an a priori choice, so say I will use 5 factors or 6 factors, or you can try to determine somewhat optimally the number of factors in your model. So the first possibility is basically to use the fraction of variance explained by R factors. So these again, sorry about this. Okay, so we were saying we want to choose how many factors to put into basically our model. So the first possibility is to look at the fraction of explained variance. The second possibility is to use information criteria. So basically something like AKIK or BIC, where you need to use a different penalty function in this specific case. So for example, Bai and Ng have more details on how to do this thing. And the third possibility, that is a little bit more messy, is to use testing. And so basically in this paper by Capetanius in JBS you find more information about this. But from a practical point of view, this first method typically works pretty well. And so basically the software typically will give you the fraction of variance explained by each principal component order. So maybe the first one explains 20, the second one 15, the third one 10. So when you arrive at getting at least 50% of the overall variance, that is a very good rule of thumb, okay? Another issue is, in particular for forecasting, but even more for structural analysis, it is better to use more factors, so a number of factors that is larger than the true value, rather than a number of factors that is smaller than the true value. Because if you use too many factors, basically you preserve unbiasedness and all the properties of the factor estimators, while if you have too few factors, it's like a case where you have omitted variable, and so basically you lose factor consistency, you introduce bias, and so basically for this reason it's better to put a few more than a few less. Now, in this slide, I am just trying to give you an idea of what you are doing in practice with this principal component estimator, okay? So basically, imagine that you have a simple model where you have n axis and there is a single factor. And you want to estimate this factor ft that is common across all of your x variables. So what could you do? Well, you could just take the sample, the cross-sectional average across n of your variable for a fixed t. So for each fixed t, you take the cross-sectional average, and so this is basically what you get. Now, what happens? These EIT, these are the idiosyncratic errors, so they will be either completely uncorrelated or very little correlated across variables. And so when you make n, the number of variables that you are considering, very large, basically this average of the idiosyncratic components will disappear, will go to 0. And so you see that then this implies that your sample average xt bar will converge to the factor multiplied by just this term here, that is an average of the loading. So it's just a rescaled factor. And so this is explaining that basically these simple cross-sectional averages is consistent up to a scale factor lambda bar for the factors, okay? Now imagine that you do a regression of xit on these x bars, on your estimated factor. You see that also the OLS estimator for the loadings converges, and in particular it will converge to lambda I divided by lambda bar. And so if you put together this feature of the estimator of the factor and this feature of the estimator of the loading, so if you just put them together, you see that basically you can consistently estimate lambda multiplied by f, that is the common component. And this common component is what you would use for forecasting. And so this tells you that basically in this simple case, just cross-sectional averaging works. So what are you doing with principal components? You are doing basically exactly the same, but instead of taking a simple cross-sectional average, you take a weighted cross-sectional average, where the weights are such that the resulting factor estimator tries to explain as much variance as possible as this is the target that you are giving. Okay? But so these principal components, you can think of them as a set of weighted cross-sectional averages. Okay? And you see that they work because by taking the cross-sectional average, when the number of variables or units is very large, the average of the idiosyncratic component will go to 0. And so these cross-sectional averages will give you a consistent estimator for the factor up to this proportionality constant, that is this lambda bar in the case of this simple example. Okay? This is again why basically these principal components are working. So let's see, now I'm having another little trouble with the computer, solved. So let's go to the next slide. So what are in general the properties of this principal component estimator? So the first bullet point is what I just told you. The second bullet point is basically telling you that these PCAs are consistent and with a proper standardization that is a function of square root of t and square root of n, they also have an asymptotic normal distribution. Okay. Now, one issue is that in the second step you are regressing the axis on the estimated factors to get estimator for the loadings. Now, you know that when you use generated regressors, so the estimated factors in our case, often you have problems. Okay, and the generated regressors typically makes OLS inconsistent. In this case, we are lucky, and we are lucky in the sense that if the number of variables that you have is very large, so technically if square root of t over n goes to 0, then basically you do not have problems of generated regressors, and you can treat your estimated factors as if they were true factors. Okay, and so this is basically helping quite a lot in empirical application. What remains a little bit a problem is what you see in this final bullet point. So it is when the factor structure is weak. So basically if the elements of the lambda matrix, the matrix of the loadings, are all very close to 0, or they are going to 0 when t goes to infinity. So in this case you have troubles, but this is a kind of very peculiar case for economic applications, because we would expect that again our large set of macro and financial variables anyway will still be driven by the common shocks that are underlying the factors. Okay, and so we do not have to worry about this bullet point. Now, how about using these estimated factors for forecasting? So here, what you have in mind is that you have a target variable y, that is what you want to forecast. Now, in principle, y depends on all the many n variables in x. But the problem is that if n is very large and possibly is even larger than the sample size t, you cannot just do a regression of y on all of the x's. Okay? You could do a selection of the x's, but again, when you have many x's, also the selection is not so simple. So what you could do is to summarize the x's with the factors, with little f, and this will be an efficient summary as we have seen, and then basically you relate your target variable of interest directly to the factors. And so you follow this two-step procedure. So first you extract the information from the x's, this will be your estimated factors, and then you regress y on the factors. And so basically you use these estimated factors as if they were any common explanatory variable. Okay? Typically you see that you use direct estimation, so you regress yt on ft minus 1, you get the OLS estimators beta hat, and then you construct your forecast for yt plus 1 by multiplying the estimated factors ft by the estimated parameters beta hat. Okay, and so it turns out that factor forecasts constructed in this way have some optimality properties, and in particular asymptotically. So when you have a very large cross-sectional n, so many variables in X, we have already seen that the estimated factors converge to the true factors. When you also have a large sample size, capital T, beta hat will converge to the true beta. And so basically when you have both a large n and a large t, these empirical forecast f hat, b hat will converge to the true forecast f multiplied by beta. Okay, and so this will give you optimality for this type of forecast that you get. Now, how about the Forni et al. Approach? Now, in this approach, you see that the starting model is a little bit different from what we had before, in the sense that here you work with the UTs, so directly with the shocks that were generating our factor. So this is a proper, if you wish, dynamic model where you acknowledge that what is driving your variables xt is basically a linear combination, dynamic linear combination of the little r shocks that are driving all of your variables. Okay, so they start basically from this setup, and then they have a set of technical conditions on the properties of the common component and of the idiosyncratic component. Okay. Now, in this case, they also emphasize the fact that you can have a smaller number of shocks, ut, than number of factors, r. So this becomes relevant not so much for forecasting, but if you want to use these factor models for structural analysis. So what's happening? Well, basically, it's, let's say, if you look at this set of equations here, so this is a case where now xt is driven both by ft and by its legs, so by ft minus 1. So what you could do is put ft and ft minus 1 into this vector that I'm calling gt, and then you can rewrite this model here in terms of the gt. And so you see that if you write your model in terms of the gt, you go back to the static factor formulation that we have seen talking about the Stoker-Watson approach. However, this is a particular formulation because now gt includes your two factors, ft and ft minus 1, but basically both ft and ft minus 1 will be driven by the same shock ut. So these uts that are the same that we have seen before in the slide for the Forni et al. Approach are typically called dynamic shocks, and instead the factors are called the static factors. So what can happen is that you have a larger number of dynamic factors, you have a larger number of static factors. GT would have two factors in this case, so more factors than dynamic shocks. UT would be a single shock. Okay, so this is something to take into account, and it's something that complicates a little bit the estimation of this dynamic version of the factor model written as Forni et al. Write it. Okay. Now again, without going into the details of the method because it gets a little bit messy, what they do is they use what are called dynamic principal components instead of the static principal components to estimate the factors. Okay. Then also in this setup, you have various ways to choose Q. So in this case, to choose the number of dynamic shocks. And again, you can do it either with formal methods like information criteria or with informal method that you see in this first bullet point. But again, it gets a little bit complex, so we can skip it. Now, for forecasting, basically, again, this is a little bit technical, but the basic procedure introduced in this first paper by Fournier et al. That came out in 2000 in the Review of Economic and Statistics. So this approach is not suited for forecasting because basically when you estimate your dynamic factors, you use not only the contemporaneous values of the axis, as in the static principal components that we have seen before, but you also use legs of the axis and leads, so future values of the axis. And so basically, since you are using the future values of the axis, you are using future information, and so basically you are using future information to estimate your factors, and so you cannot do a kind of real-time implementation of the method. So it turns out that you can use a different estimation method that is described in this other paper that you find in the second bullet point of this slide, which again is even more complex than the first method. So just to tell you to be aware about this, and then in case you want to implement it, you can just go to this second paper by Fournier and co-authors and see what exactly they do. Okay. Now, so far we have said, if you have a small factor model, you can use the Kalman filter. If you have a large factor model, you can use static principal components, dynamic principal components, and before I told you, you cannot really use the Kalman filter because computationally it gets too complicated. However, it turns out that you can do something that is pretty similar to the Kalman filter. And so it is this quasi maximum likelihood estimator. And so this was proposed in these two papers by Catherine Dawes, Domenico Giannone, and Lucrezia Reichling, that again you find in the references at the end of the presentation. And what is the idea here? So the idea here is to go back to a parametric version of the factor model. So basically, when we talked about Stocker-Watson and Fournier et al., we only had equation 2, so only an equation relating the variables to the factors, but we didn't say anything about the generating mechanism of the factors. Instead, in this quasi-MLE estimator, you need to go back and add your VAR for the factors that we have seen before. And so basically equation 2 and 3 are again a state space form like the one that we have seen for the small n case, except that again in this case the number of variables in X will be very large. There is also an additional complication with respect to the simple state space form that we have seen before, and this is related to the fact that you see that in the equation for the factors you have b times eta t, and so here the idea is that eta t are these dynamic shocks, and so you can have fewer dynamic shocks than, as I was telling you, factors. And so if Q is the number of dynamic shocks eta, and if R is the number of factors F, you have that Q is less than or equal than R. Okay. Now, how do you estimate this model? So, like in the case of the Kalman filter, you have to use a sequential procedure that is basically described in the next slide. So, basically, you initialize your procedure by estimating the factors by principal components. Okay, and at this point, you have a preliminary estimate for the factors and for the loading matrix. And basically, you use these preliminary estimates of the factors and of the loading matrix to get an estimate, you see here, of the idiosyncratic errors, so of psi t. Next step is you have your estimated factors. So you use the estimated factors instead of the true factors to estimate the VAR for the factors. And so at this point you will get residuals from this VAR for the factors, and you will also get the residual covariance matrix that is in this second line of the second bullet point. This will be called the sigma hat of Z. Now, the problem is to estimate the B matrix that gives you the effect of the dynamic shocks ZT on the factors, okay? So for this, basically, you need to apply what is called an eigenvalue decomposition, which is what you find in the very final line of this bullet point number 3, okay? At this point, you can apply the Kalman filter, or the smoother if you wish, and this will give you a new set of estimated factors, okay? So you go back to step 1 and you iterate until basically the estimates of the factors that you get stabilize, okay? And so you get your improved estimates of the factors with respect to the starting values that were the principal components. And so you construct your forecast basically either using the direct approach that we have seen talking about, the Stocker-Watson approach, but using these refined factor estimates, or since now you also have your VAR for the factors, you can use an iterated approach where basically you use your VAR for the factors to get estimates for future values of the factors, so this f at t plus h here, and then basically you use the equation that links the x's to the factors to construct your forecast. Okay, so this is basically how this parametric approach works in the large N setup. So we have seen when n is larger, static principal components, dynamic principal components, this quasi-maximum likelihood estimation process that is closely linked to the Kalman filter. Fourth option is to use what is called a subspace algorithm. Okay, so let me skip this because we do not have so much time. And then again, if you want to know more details, you can just go to this paper that you find cited in this slide. Okay, so let's skip also this slide. Let's skip also this slide, and let us move instead to the slide that you see that is basically trying to compare these 4 alternative estimation methods that we have now. So principal components, dynamic principal components, maximum likelihood, and this subspace algorithm. Okay. So in this paper that where we introduce the subspace method, we also run this Monte Carlo. So this is the process that is generating the data. You see it's even a little bit more general than the one that we have seen so far, because the factors are basically generated by a vector ARMA model here instead of a pure VAR model. And so we look at different combinations of number of variables n and number of observations t. We look at different values for the A matrices, the B matrices, and the C matrix. We look at different number of factors, so we try to make it basically as extensive as possible. And for each of these designs of the data generating process, we estimate the factors using one of these 4 methods. So either estimate by PCA or DPCA or maximum likelihood or subspace algorithm. So in the appendix B that you find at the end of the slides, you find more details both on the DGP and on the results. So here I just wanted to summarize the main findings, okay? So the main findings is that are that at least in this Monte Carlo, that again is however very general, the dynamic principal component is a little bit worse than the static principal components and this subspace algorithm. Subspace algorithm is a little bit better than principal components, but the differences are very, very small. And so subspace is also a little bit better than maximum likelihood, which in turn is a little bit better than principal component, because this iteration that we have seen in like 2 or 3 slides ago was basically helping to further improve the principal component estimator. However, the main message, and again, if you look at the appendix with also tables, it will be more clear, is that all the methods work very, very, very well to estimate the factors and to estimate the common component. So given this, that all the methods work so well, the suggestion is to use the static principal components, so the first method that we have seen, the one proposed by Stock and Watson, just because it is very, very simple. So in MATLAB, you only have to take out eigenvectors from x prime x, and even in EViews, you can program the model to extract the principal component. Okay? Now, how about the forecasting performance at this point? So once we have understood how to estimate our factor model, what can we say about the forecasting performance? So at this point, there is a very large number of papers using factor models for forecasting macroeconomic and financial variables. So you have the early applications by Stock and Watson for the US, and I did a paper with them on factor forecast for the euro area. I've also done work on basically Eastern European countries, because that is an interesting case where you have many variables, but the temporal dimension is short. And also, since these countries were undergoing transition from the former communist regime, you also have a lot of problems of parameter instability. So it's a really kind of tough playing ground. And even in this context, the factor forecast worked reasonably well. Okay? Then there is this 2008 review by Ackmeyer and Ziegler that do a kind of meta-analysis, and there is Stock and Watson for a survey of earlier results. Okay. Now, all of these papers were typically focusing on short-term forecasting, so 1, 2, 3 steps ahead. Now, these models have been used also for nowcasting. So, as you know, this means basically getting an estimate, for example, for GDP for the current quarter, so before it is released. And so here you have a set of additional complications, like, for example, working with mixed frequency data and so on. So in this paper, again, with these two people from the Bundesbank, Vladimir Kuzin and Christian Schumacher, we compare many alternative factor models for nowcasting, and we show that they work very, very well also for nowcasting. Okay, so again, this can be relevant for those of you that have to do this on a day-by-day basis, like to give an indication of where the economy is going before the Statistical Institute releases the data. Okay. So this is a summary from the Ackmeyer and Ziegler paper, and basically what they are telling is just a comparison of results for UK and US. So of course it is important that you try these models, because still it is not necessarily the case that they give you optimal forecast for all the variables, for all the countries, for all the time periods. So the suggestion is just to have them ready in your toolkit that basically you use for forecast. Okay. Now, how about structural analysis? So the idea is that, as I told you at the very beginning, what you could do is you could complement your factor model that links the variables axis to the factors with a VAR model for the factors. Okay? The factors themselves are unobservable, but now we know that we can estimate them. And so the idea is that you can use a structure telling you that basically the point is that at this point you have a VAR for the estimated factors that you can use as a structural VAR to back up structural shocks, and so you get the transmission of the structural shocks to the factors via the VAR for the factors, And then once you have the impulse responses for the factors to specific shocks, you can plug them into the model for the axis, and this gives you the dynamic response of the axis to the factors, in particular to the shocks that are driving the factors. Okay, and so this is kind of nice. And again, one of the first applications is this paper in QJE by Bernanke, Boven, and Elias, where they studied the transmission of monetary policy to a large set of variables. Okay, and then there are a set of extensions, and again here you find references on how to get them. So let's see a little bit better what Bernanke, Boven, and Elias were doing. So as I was telling you, the idea is that you move from a reduced form VAR to a structural form VAR. So exactly as you would do with the normal VAR once you have estimated the factors. And so you use this VAR to back up your structural shocks that now are the use. Okay? And then you compute the responses of the factors to the use, and then the responses of the axis to the use via the factors. Okay. Now, Bernanke, Boven, and Elias do something a little bit more complicated in the sense that they want to impose that one of the factors is observable and coincides with the federal funds rate. Okay, so what you find in the subsequent slides is the method that Bernanke, Boven, and Elias have devised to impose that one of the factors is actually observable rather than being unobservable. Okay, so this is basically what they do. In particular, you can look at the second bullet point here. So the idea is that you have estimated your G+1 factors, then you split the data set into the slow-moving variables, that are those that do not react contemporaneously to the monetary policy shock, and fast-moving variables that instead can move, can jump, so they can move instantaneously. Okay. So typically in the set of slow-moving variables, you put real activity measures, prices, deflators, and this type of variables. Okay. So at this point, you have your variables split into two sets, and basically you only use the slow variables to construct G principal components. Okay. So you have your F factors that are based on all the variables, and you regress them on this alternative set of factors that are only based on the slow-moving variables. And at this point, an estimate of the factors that you want, they show that it is given by the fitted value from this equation. So by A hat multiplied by F hat slow. Okay. So at this point, you have your set of factors Ft that are made up of this factor F hat, that are what you get by principal component after the cleaning for the interest rate, plus the observable factor that is IT. Okay, and they put them in this order in the VAR, and so at this point you can just do, since you are only interested in getting the monetary policy shock, you can just do a Cholesky decomposition of this VAR, where you have the first estimated factor, second estimated factor, and then at the end you have your observable factor that is the interest rate. Okay? And so, of course, rather than doing Cholesky, you could do any other type of structural identification. So you could put short and long run restrictions, you could put sign restrictions. Basically, all the machinery that you have available for structural VARs can be applied in this context. So what do you do next? So final bullet point. Again, first you get the responses of the factors to the structural shocks. Okay. And then instead you get the responses of the x variables that will be equal to the responses of the factors pre-multiplied by the lambda matrix. Okay, and so this is basically all that you want. By the way, little parenthesis maybe for Alberto. I have realized the problem why I lost the connection and it seems that this Adobe system conflicts with Skype. So now I've closed Skype, so hopefully it works, but perhaps this was the problem. Anyway. So let's go back to more interesting stuff. So at this point, we have got the identified monetary policy shocks, and we know how to, oops, maybe you don't see me, so now you should also see me. Okay, so at this point, you also know how to get the structural shocks. And so you can get your dynamic responses of the variables that you are interested in to the dynamic shocks. So what you find reported in this next slide is the response of the federal funds rate of GDP and of the GDPlator to this identified monetary policy shock. So the bold line is coming from the methodology that I told you, and instead the dotted line is coming from this paper with Eichmeier and Lemke, where we develop the time-varying version of the FAVAR. And so the dotted line is an average of all the responses computed over basically 20 years of data. And so from here you see that the average responses are not so different, but if you do it in a 3D graph that you can see again in this other paper with Eichmeier and Lemke, you will see that over time there are differences. And in particular, what you find is that the response of the nominal variables was much stronger, so they were much more reactive to monetary policy at the beginning of the sample rather than in these more recent samples. So the nice thing of this approach is that at this point you can compute the reaction of all the many variables that you have put into XT. So for example, in this slide you find the reaction of consumption, investment, industrial production and employment. And you see that they are all kind of theory consistent. So all of these variables are basically decreasing after a monetary policy shock. You can also compute the reaction of a set of price measures. So here you see you have a very little price puzzle for PPI and a little even less for PPI and for the PCE deflator. And instead you get a much more delayed reaction of unit labor costs and so on. Okay. So basically, again, to conclude, this is just to show you that with these factor models you can do quite many things. So the basic analysis are concerned with using these models for constructing coincident indicators, leading indicators, financial condition indices, and for this you only need an estimate of your factor. Then you can do forecasting, where basically you just plug in your estimated factors into standard regression models and construct your forecast like this. Or you can go even one further step and use your factor models for doing structural analysis. So in this case, you use your estimated factors into a VAR model, and you use the VAR for the estimated factors to identify structural shocks, and then you compute the dynamic reaction of the factors to the structural shocks, and then you use the responses of the factors, multiply them by the loading matrix, and this gives you the reaction of all the n variables that you are studying to these identified structural shocks. Okay, I think, stop here. I don't know if there are any questions or doubts or curiosities.
Everyone's microphone is open right now, so they could either enable their microphone and ask directly or write in the chat window.
Thank you. Well, I guess this was quite a lot of material. Plus, I guess it's close to lunchtime for you, so it's understandable.
Some people
that
have work.
there is little reaction.
For example, we just finished a book where a team from the Banco Central of the Dominican Republic use a structural method are the same view, I guess, Elizabeth, Bucacos from Uruguay. And I don't know what is the methodology that those of this year's research network are planning to work on.
Oh, thank you. I just received some thanks. Thank you very much. It's a pleasure. I'm looking forward to working with those of you on this project.
I think we all coincide that there are many. This is a great summary of the work, and also it will be very useful because you point us to different references
I hope.
to further. Yeah.
Thank you. Thank you. Yes. And then for those of you that are coming to the conference in September, we will have this class together on mixed frequency models. And in there, we will also go back and talk a little bit about mixed frequency factor models. So maybe that can be another idea. Okay, so here I see an interesting question. What do you think of applying factor analysis instead of principal components in order to get the factors? So that is indeed a very good idea. The only problem is to derive the theoretical properties of the estimators, in the sense that typically, at least as far as I know, factor analysis typically was applied to IID data and not to time series. And actually, a lot of work that Stock and Watson had to do, and some of it I had the pleasure to share with them, was to derive the theoretical properties of this estimator and of the resulting forecast. But this is indeed quite interesting. So also, again, I don't know, but if some of you are also working on big data, there are also versions of factor analysis and of principal components that work on sparse matrices like those that you have in big data. So that is also something that could be tried. Okay, so now I read something on how hard to get the estimation. So again, for the simple principal components, it is pretty easy. Again, even in eViews, it can be done. You define just a group object with all the variables, and then eViews can extract the principal components for you. Where it gets more messy is, for example, to implement these dynamic principal components. Or if you want to do a little bit more sophisticated things like this pseudo Kalman filtering that gives you the quasi maximum likelihood estimator. That gets pretty difficult. But there are some papers like those published in the Journal of Applied Econometrics for which you also can get some basic code from the Journal of Applied Econometrics code archive. And so maybe that could give you an idea of a starting point if you want to implement it. Oh, I see. So what? Okay. Now the second part of the question arises. So how difficult it is to estimate when you add dynamics on the idiosyncratic error. So if you just want to get the static principal components, they will be consistent even if you ignore that you have correlation in the idiosyncratic errors. If you want to improve a little bit the estimation, instead you should go to one of these more parametric versions of the models, and then it can get a little bit more messy, let's say. But it's more important to put say an AR1 component in the error when you use the model for forecasting rather than when you use it to extract the factors. Also in this case, it's not such a major issue. Okay, so I do not see other questions coming. So again, thanks a lot. It was a big pleasure, and looking forward to meeting all of you again, either at SEMLA in September or by email, Skype with some of you, or hopefully
Thank you very
in
much,
conferences, seminars.
Massimiliano. So I guess some of the teams from the joint research will be in contact with you. And then, as Massimiliano is mentioning, we have two events in September. One will be a workshop of the Joint Research Network on inflation expectations, and the second one will be a course and roundtable that we will have with the IMF, and the information will be going to your institutions in a couple of weeks. So through the formal channels, the information will arrive to the institutions, and then the institutions usually assign the participants, trying to get the better match for what the content will be. So again, thank you very much, Massimiliano, and thank you to all of you who participated today. Thank you.
Bye bye, everyone.